Good morning to all. Welcome to the course Operations Research, for which the course tutor is Professor Kusumdeep, IIT Roorkee. Myself, Jayana Gasri, PMRF Research Scholar and a teaching assistant to this course from the Department of Mathematics and Statistics, University of Hyderabad. Coming to our course, what is an operations research? Operations research is a scientific approach for making decisions to the problems solving in real life in a way of formulating mathematical models. And in the development of operations research has been entered successfully in many different areas of research. In the research for military, government and industry, and also in many other various fields like in agriculture, in finance, and in industry, and in marketing, in personal management and production management, LIC, and so. In agriculture, we can see the operations research is useful in the way of optimum allocation of land to various crops in accordance with climatic conditions. In finance, the operations techniques can be fruitfully applied to maximize the per capita income with minimum resources, or to find out the profit of company, or to determine the best replacement policy. In such a way, operations research is helpful in the finance sector. And in industry, the operations research is useful to make the decisions about optimal allocation of various limited resources such as machines or men, material, money, and time, and so. And likewise, operations research is useful in many different fields. And next, coming to the main phases of operations research. The procedure for an operations research study is generally involved in different phases. In the first is formulating the problem. That is, before proceeding to find a solution to a real life problem, first of all, one must be able to formulate the problem in the form of appropriate model. To do that, we need a following information, that is, who has to take the decisions, or what are the objectives, and what are the ranges of the controlled variable, what are the constraints or restrictions of the variable that may affect to the possible solutions. And next thing is to construct a mathematical model. The mathematical model is used to reformulate the problem in an appropriate form which is convenient for the analysis. For that, this mathematical model involves the mainly three parameters, that are decision variables, objective functions, constraints, or restrictions. And the decision variables are the variables which has to be determined for the problem, and objective function, that is what is to be maximized or what is to be minimized, and constraints are the conditions which the decision variables or decision parameters should satisfy. Of course, we are modeling this mathematical model to find out the solutions to our problem. So finally, our main interest is to find the values of the decision variables, for that to maximize or minimize the objective function. And next, here is the question, that general formulation of LP. In building a constructing a mathematical model, one must be know that there are many ways of constructing a mathematical model. That is, one of these is uh, linear programming problem. That is LP. That means whenever the constraints and also the objective function is in linear, then we can use a linear programming problem. Here you can see the general formulation of this linear programming problem. This general formulation of linear programming problem involves to find the values of the decision variables. Let us suppose that let us suppose that x1, x2, and so on xn. These are the n decision variables. So to find the values for the decision variables, to minimize or maximize the linear function, that is an objective function, which should be in maximize or minimization type, then write that in the form of linear function, where these x1, x2, xn are the decision variables, so that the function z is called an optimization function, which is in the form of maximizing or minimization type, and subject to the constraints that are take a11 x1 plus a12 x2 plus and so on plus a1 and xn. Because there are the n decision variables, we have written a linear form constraint, which should be in less than or equal to type or equal to type or greater than or equal to type, and less than or equal to b1 or greater than or equal to b1 or equal to b1. This is called a constraint, one constraint, which involves the all decision variables and in the linear form. And other is a21 x1 to x a2n xn p2. Likewise, we are supposing there are the n constraints, so that these are the m inequalities or equations. M n xn p. So all these are the m constraints. The constraints can be in linear form or in inequalities that are less than or should be in linear form, and that are inequalities of less than or equal to type or greater than or equal to type, or even in the form of equations. And finally, there is a non-negative restriction, that is the decision variables must be non-negative. There are the n decision variables, so there are n non-negative restrictions. And the left hand side bj, so suppose j is equal to 1, 2 and so on n, these should be these are also should be restricted to non-negative values. So this type of formulation can say it is a general formulation of LPP, where to find the solutions to the decision variables x1, x2 and xn, and the objective function is in the maximization or minimization type and subject to the constraint and non-negative restrictions. So you can say, if there is a question, linear programming problem is a constraint optimization technique for economic allocation of limited resources, mathematical technique, or all of the above. So previously we were saying that linear program, general formulation of a linear programming, where we observed that optimization is maximum or minimum type, so that there is an optimization function. So that is used for the optimization technique, and which involves the constraints. Based on those constraints, we are optimizing the function. So we can say that the LPP is a constraint optimization technique, and it is also a technique for economic allocation of limited resources, as A1, A2s are the, can say those are the resources available. With the limited resources, we are using the technique for an allocation or optimum allocation. And it is a mathematical, of course, it is a mathematical technique. So I can say that answer is the all of the above. And next, these are the two definitions for slack variables and surplus variable. Then the slack variable is if the constraint has the less than or equal to type, then in order to make it an equation, we have to add something positive to the left hand side. That is called a slack variable. For example, here you can see there is a constraint x1 plus x2 of less than or equal to type. Then to make this constraint into an equation, we need to add a positive quantity, that is I am adding here is a an x3 which is a positive quantity to the left hand side. Then I am converting the inequality into equation. For that, this variable is called a slack variable. And of course there is a non-negative restriction, that is x1 greater than or equal to 0, and also the slack variable is must be non-negative restriction. In the same way, if the constraints have greater than or equal to sign, then in order to make it in an equation, we have to subtract something from the left hand side. That means, for example, we have x1 plus x2 greater than or equal to 4, which is a greater than or equal to type constraint. Then to make it into an equation, we have to subtract the quantity which is called a surplus variable. So here it is a surplus variable. Likewise the non-negative restriction and x4 greater than or equal to 0. It is just named it as an x4. You can also name it as x3, x5 or something, but we have to subtract it from the left hand side. So it is called a surplus variable. Why? What is the use of these slack variable and surplus variable? I will tell you the next. Here is the question that in the standard form of linear programming problem, which of the following is not true? Before going into the question, first we have to know what is the standard form of LPP. Okay, okay. This is the standard form of linear programming problem is used to develop the procedure for solving general linear programming problem. Before we have seen the general linear programming problem, how it looks like. So now we see what are the characteristics of standard form. The first thing is all the constraints should be converted into equations. That means if the constraints are less than or equal to or greater than or equal to type, then we should be convert into the equations type by using slack or surplus variables. Slack or surplus variables. We say if the constraint is less than or equal to type, then in order to make it an equation, we use the slack variable. Or if it is a greater than or equal to type, then to make it an equation, we the subtract the inequality by surplus variable. And next thing is the right hand side of the elements of the constraints should be non-negative. That means we see in bj's in the left hand side that all the bj's should be non-negative. And the third is all the variables must be non-negative values. That means the variables means in our model xi and also the xn. Xn is the slack or surplus variable. All of these x's and xn's should be non-negative in the standard linear programming problem. And if the objective function is in minimization type, we have to convert into the maximization type. That means the objective function should be in maximization type. Here you can see if the objective function is minimization type, that is the minimum of z, then we need to convert into maximization type by considering in this way. So here, after saying these all the characteristics, we can see each of the option is not correct. First thing is optimization function should be maximum. As we seen that in the last property, the optimization function should be in max type only. And next, the constraints should be equations. As here, we are converting the inequalities into equations, and the RHS of the constraints should be greater than or equal to 5, so that the next option is also correct. And can see the third option, when we see the constraints should be less than or equal to 10. Previously, we had discussed that the constraints should be converted into equations. So this is the meaningless. And finally, the decision variables shall be non-negative. That means, yes, of course, here we have seen the decision variables and also slack and surplus variables should be greater than or equal to 0, so that this is also correct. So finally, our option is A equal to C is the required option. Next, here is a question that express the given LPP in the standard form. Previously, we had discussed that the objective function should be in maximization type. So that here we observe the objective function is in minimum type. So we need to convert this into the maximization type. Here I am writing in the maximization type minus x1 plus 2x2 minus x3. Since we know that minimum function of that is equal to minus maximum of minus 2. Here I have taken the minus, or can write maximum of z star, where z star is equal to minus z, since z star is equal to minus 2. So objective function, formatting an objective function is done. And next, coming to the subjective constraints, you have to convert the subject to the constraints into the equation. And one more thing is uh, to know that the left RHS side of the inequality should be non-negative. Here we observe that in the first inequality, or the objective first inequality, the LHS is in negative form. So we need to convert it into the positive by multiplying minus 1 on the both sides. So that minus 2x1 minus 3x2 minus x3 less than or equal to 4. And other inequality 3x1 plus 5x2 plus 2x3 greater than or equal to 7. So we need to convert this into equations. Here we observe that the first inequality is in the less than or equal to type. First inequality is in less than or equal to type. So we need to add a surplus variable to the LHS to make it into equation. And next inequality is involved in greater than or equal to constraint. So to make it into equation, you have to subtract it with the surplus variable minus x5, that is equal to 7. Here x4 is the slack variable and x5 is the surplus. So to convert the inequalities into the equations, we need the slack and surplus variables in a standard form of LBP. And another thing to identify here is x3 is unrestricted in sign. Whenever the variable is unrestricted in sign, then we can have to change that variable into the difference of other variables. That is x dash, x3 double dash are the two other variables. Then we have to replace the x3 with the difference of other variables in the entire problem. x3 dash minus x3 double dash plus x4 equal to 4 and 3x1 plus 5x2 minus plus 2 into So finally you can write that non-negative restriction that x1 greater than or equal to 0, x2 greater than or equal to 0, and also the x3 dash and x3 double dash greater than or equal to 0. So we had written the given LPP problem into the standard form. Whatever the standard form consists, the standard form must be have the maximization type, that is maximum of, here we have written converted the given problem into maximum type, that minus x1 plus 2x2 minus x3. Here x3 is x3 dash minus x3 double dash, and we have converted the inequalities into equations, x3 dash minus x3 double dash plus x4 equal to 4, and other is minus x5 equal to 7. And non-negative restrictions, x3 dash x3 double dash greater than or equal to 0. So for the given problem, we can say that this is the standard form of an LPP. Next, here is a question that solve solution to maximization of Z. This is objective function and subject to the constraints and non-negative restrictions. And options are the solution is unique or unbounded, or multiple solution, or infeasible solution. You can say in an LPP, linear programming problem, if the variables are two, that means if the only two variables are involved in an LPP, then the graphical method is simple and easy to solve the solution. Graphical method. If there are the more than two variables, then there are the another methods like simplex. First, here you can see the procedure of graphical method. This, okay, just a minute. In a graphical method, first step is, here I am writing the graphical method. First thing is we need to change the constraints into equations. Constraints into equations. Next, to find the points of each equation, we have to put the x1 is equal to 0 and x2 is equal to 0, then find the points. And third thing is, take a graph and plot take a graph and plot the graph with the given points. And finally shade the region. Shade the region according to the given inequalities. That means if the inequality is less than or equal to type, then shade the graph towards the horizon. If it is greater than or equal to type, then shade away from the origin. Finally, find the common region, that is known as the feasible region. Common region. and find out the points to the common region, and then find the and then find the value of the objective function at these points. Value of objective function at this point. Now, by using this procedure, you can see the given problem, how to solve the given problem. Here they have given the objective function maximization type. So first thing is have to change the given constraints into equation. Here the given constraint is x1 plus x2 equal to 4. It is not converting the constraints into equation. It is just changing the constraints into equations. So these are the I am here written the equation 1 and 2. And next take the values x1 equal to 0 and x2 equal to 0. Then solve the points. Oh, here this is one thing I use first done. Next, if the point here taken x1 equal to 0, then x2 equal to 4. So the point is 0 comma x1 0 x2 4. In the same way, if x2 equal to 0, in the equation 1 we can find x1 equal to 4, so that the point is x1 4 x2 0. In the same way, in the equation 2, if x1 is equal to 0, then x2 equal to 12, point is 0 comma 12, and if x2 equal to 0, then x1, here 3x1 equal to 12, so that x1 equal to 4. So the point is x1 4 x2 0. So based on these points we need to draw a graph. The graph is in the first quadrant only. There is 0. The x-axis representing the decision variable x1 and this y-axis representing the decision variable x2. So here we observe that the point first is x1 0 and x2 4. Here it is, and x2 and x1 is equal to 4 and x2 equal to 0. So here it is. Then make a line combining these 2 points and shading the region with the help of given inequality. Here the inequality is less than or equal to type, so that we have to, if the inequality is less than or equal to type, then shade the region towards the origin. So that if we shade the region towards the origin, here it is. And taking another point, x1 0 and x2 12, here it is, and x2 x1 4 x2 0, same point, so that making a line combining these. And the next inequality is also have the less than or equal to type constraint, so that shade the region towards the origin. Then find the common region, that is here the common region is the here where the 404 is just noting the common region points A, B, C. Here we find that the points A equal to 0 4 common region points, c equal to 4 0, no sorry 0 0, and c equal to 0 4. So at the point A, if we find the value of the objective function, that is z equal to 4x1 plus 6x2, here x1 x2 are 0 0, then objective function value is 0. At the point P, the objective function value is 4 4 is 16, and at the point C, the objective function value is 24. So here we assert that the maximum value is obtained at the point C. That is the maximum value is Z, 24. So we can say that at the point C, we can attain a optimal solution. Here we observe that only a single optimal solution. So we can say that it is unique. Our option A is correct. Other options are unbounded, multiple solution, infeasible solution. Unbounded means if we share the regions, if we won't find a common region, and that means it is going to the infinity, the region is going to infinity, then we can say it is an unbounded. And if we find the same solution to an another at the another point, then you can say there are the multiple solutions. And infeasible solution means if we won't find a common region, then that is an infeasible solution. Our is unique solution, and the solution is optimal value of z is 24, and which is attained at the point 0, 4, x1 0 and x2 4. That is the values of the decision variable. And here is another question, that the graphical method of linear programming problem uses options are objective function equation, constraint equations, linear equations, or all the above. Previously you see that we just convert the constraints, change the constraints into equations. So that you can say constraint equations only, not any of the objective equation or linear equation. Finally done, and thank you.